This is the first of two videos solving trigonometric equations. Like identities, solving trig equations is a topic that you want to do a large volume of problems. Sometimes it can be difficult to see the algebra through the trig, so doing a lot of these types of problems will just make it easier for you to recognize which algebraic technique we need to do to solve these types of equations. So first here I have kind of an outline of the steps you want to take. You want to start by deciding whether the equation is linear or quadratic in form so you can determine the solution method, because we know we do different techniques depending on whether it's linear or quadratic. If there's only one trig function present, you're happy about that, and you're going to start by isolating that function. If more than one trig function is present, you want to rearrange the equation so that one side equals 0 and try to factor it. If the equation is quadratic in form but not factorable, yeah, you might have to use quadratic formula to solve it and then check that your solutions are in the desired interval. You may have to use trig identities to change the form of the equation. It may be helpful to square both sides of the equation first, but remember, if you do that, you will have to check for extraneous solutions. Anytime we raise both sides to an even power during our solving process, we must check our answers. So you want to try to get a single trig function. You need to make sure that your arguments are the same. All right, so let's try some. We want to solve each equation for the exact solution over the interval 0 to 2 pi. Anytime the directions say exact solution, we know that we are in radian. Here we have sine of x plus 2 equals 3. Since there's only one trig function present, we want to start by isolating that trig function. So we'll subtract 2 from both sides, and we get sine of x is equal to 1. Now we can easily solve for x using our inverse sine function. X is going to be equal to sine inverse of 1. So now we have to figure out where on the interval from 0 to 2 pi does sine equal 1. Well, the only time sine equals 1 is when we're at our maximum value, and that occurs when x is equal to pi over 2. That was like our warm-up problem. That's the nicest one we're gonna come across. Next, let's solve 2 cosine squared x minus square root of 3 times cosine of x equal to 0. Well, I'm happy to see just a single trig function of cosine, but notice that it shows up more than once, and one time it's squared and one time it's not. So this equation is quadratic in form, so we want to treat it like a quadratic. Now, it can be helpful to do some side work and kind of strip out the trig as we've done before. This is 2c squared minus the square root of 3 times c equal to x. And I think when we rewrite it this way, it's a little bit easier to see that we have a common factor of c that can be factored out, which would leave us with 2c minus the square root of 3. So that's what we're going to do over here, where c just represents cosine. Factoring a cosine of x out, we're left with 2 cosine of x minus the square root of 3 equal to 0. Now that we're in factored form, we can apply our zero product property and set each of these factors equal to 0 and solve. And we're basically back to the previous example, just two little problems like that. So if cosine of x is equal to 0, then x is equal to cosine inverse of 0. So we have to figure out where on the unit circle is cosine equal to 0. So that means we're moving 0 in the x direction. That's going to happen up here and down here. So the first one is going to give us x equals pi over 2. and 3 pi over 2. Now we want to solve the other linear equation. It has a single trig function, so we're going to start by isolating that cosine of x. So let's add square root of 3 to both sides. And then we'll divide by 2. That gives us cosine of x is equal to square root of 3 over 2. I'm happy to see square root of 3 over 2 because that's a known value on the unit circle. So x is going to be cosine inverse of square root of 3 over 2. Now we just have to figure out what values on the unit circle, what angle measures. Cosine has that positive square root of 3 over 2. That's the long side of a 30, 60, 90 triangle. Since cosine is positive, that means we're either in quadrant 1 or quadrant 4. So long side, short triangle. That means that we're going to have 30-degree reference angles for both triangles. Make sure that you're putting your answer in radian mode. Well, just radian. So the x is going to be pi over 6. Now don't say negative pi over 6 because we need our answer to be between 0 and 2 pi. So that second answer is going to be 11 pi over 6. There we go. 4 answers. The next equation we want to solve is cosine of 2x minus cosine of x equals 0. The first thing I notice is that I have different arguments. They're both cosine, but they're different cosines because one's cosine of 2x and one's cosine of x. So the first thing we need to do is get the arguments the same. And it's always easier to tear down a more complicated argument than it is to build one up. So we want to use a double angle formula for cosine. If you recall and look at your formula sheet, there are 3 different formulas for cosine for a double angle, and we need to choose the one that makes the most sense. There's one that contains just cosine, one that contains just sine, and one that contains both sine and cosine. Since the other trig function in this equation is cosine, we want to use the double angle formula that only has cosine involved. But we're going to replace cosine of 2x using our double angle formula with 2 cosine squared x minus 1. And then we have that minus cosine of x on the end. I'm going to rewrite this in descending order. 2 cosine squared minus cosine minus 1. And this is a quadratic trinomial, and we do want to factor it, but maybe easier to do the factoring over on the side without all the trig words in there. So this is 2c squared minus c minus 1. And when we factor that, we're going to get 2c plus 1 times c minus 1. So now let's plug the cosine back in to the actual problem. 2 cosine of x plus 1 times cosine of x minus 1 equals 0. And now that we're in factored form, we use our zero product property to finish solving. 2 cosine of x plus 1 equals 0. And cosine of x minus 1 equals 0. For each of these, we have a single trig function, so we're going to want to isolate the cosine and then use inverse cosine to solve. 2 cosine of x is going to be equal to negative 1. Cosine of x is going to be negative 1/2. We know that's a value on the unit circle, so I'm happy to see that. X is going to be cosine inverse of negative 1/2. So now we need to figure out where on the unit circle does cosine have a value of negative 1/2. 1/2 is the short side of a 30, 60, 90 triangle. The cosine value is negative 1/2, so we know we have to be in quadrants 2 or 3. So short side for the x, long side for the y, so that's going to be a 60-degree reference angle for both of our triangles. Writing each of those angles in radian mode, we get x to be 2 pi over 3 for the first one, and 4 pi over 3 for the second one. Now let's solve cosine of x minus 1 equals 0. Isolating the cosine, we get cosine of x equals 1. So that means x is going to be cosine inverse of 1. We want to think, where on the unit circle does cosine have a value of positive 1? Well, that only happens one spot, and that's right here. So x is equal to 0. Now, you really got to be careful with these answers that are happening at 0. You want to go back and look at the interval they gave you to solve on. You'll notice that our interval from 0 to 2 pi, it's including 0 and excluding 2 pi. Sometimes it's the other way. Sometimes they'll exclude 0 and include 2 pi. So make sure you're paying attention to that, especially at 0, so you don't get it marked wrong, even though you had the right idea. All right, last one for this video. We want to solve the equation and give all exact values. You'll notice that I bolded all for you there, because sometimes people miss it. Anytime it asks for all solutions, that means that you're going to find the solution, but then you want every single angle coterminal to that angle. And exact tells us we're in radians, so we're going to get our answer, and then to get every coterminal angle, we're going to add 2 pi n, right? Because 2 pi is one trip around the circle, but in order to make sure that we're doing like entire multiples of 2 pi, we then have to go on and specify that n is an integer, and that's what the shorthand means. That weird looking e means is an element of, and the boldface z is the abbreviation for integers. And we don't have to say plus or minus, because integers are both positive and negative counting numbers, so that'll add 2 pi and subtract 2 pi for us. All right, secant squared of theta over 2 equals 2 secant of theta. Well, I noticed that everything's in terms of not sine, cosine, or tangent, which is what I have all my formulas, so it's likely I'm going to have to rewrite this in terms of sine and cosine. I also noticed that my arguments are different. One's theta over 2 and one's theta. I'm going to have to get those in terms of the same argument. So we're going to have to use a half angle formula, but we have to get it in terms of a trig function that actually has a half angle formula first. So I'm going to rewrite this cosecant squared of theta over 2. I'm going to do two things. I'm going to turn cosecant into sine of theta over 2, and I'm also going to put the squared on the outside. On the right side, I'm also going to turn secant into cosine. So this is going to be equal to 2 over cosine of theta. Well, we got to get the arguments the same. So we're going to use our sine half angle formula on the left. And that's plus or minus the square root of 1 minus cosine over 2. And now we're going to square that left-hand side. Remember, when you are squaring a fraction, you can square the numerator and square the denominator separately. So when we square the numerator, we're going to get just 1. Now in the denominator, we have a plus or minus. When you square a plus or minus, it just turns plus, because squaring a plus is plus and squaring a negative is plus. So that just disappears. And when we square a square root, those also cancel out. So we're left with just 1 minus cosine of theta over 2 in the denominator. What we have now is a proportion, 1 fraction equal to 1 fraction, and I always like to see a proportion because then I can cross multiply. So we're multiplying this whole big ugly fraction in the denominator here by 2. That's going to give us 2 times this whole fraction, 1 minus cosine of theta over 2, equal to cosine of theta. And this 2 out in front is like over 1, so it can actually be simplified with the 2 in the denominator, leaving us with 1 minus cosine of theta equal to cosine of theta. And this is a much better situation than we were in, where in terms of the same trig function, we have the same argument. Notice that both of our cosines are linear. We don't have an exponent on them. So we're going to treat this like any linear equation where we get all the variables on one side and all the constants on the other. So let's add the cosine of theta from the left over to the right side. This gives us 1 equals 2 cosine of theta. Isolating the cosine, we'll divide by 2, so 1/2 is equal to cosine of theta. 1/2 is on the unit circle, so we're happy to see that. Theta is going to be cosine inverse of 1/2. So now let's figure out where on our unit circle cosine is equal to 1/2. That's the short side of our 30, 60, 90 triangle. 1/2 is positive, so that means that we are in either the first or the fourth quadrant. So short side for the x, long side for the y. That's a 60-degree reference angle for both of our triangles. So for the first one, theta is going to be pi over 3, and the second one is going to be 5 pi over 3. But remember, in the directions, we're looking for all solutions. So for each of these, to get our final answer, we're going to have to add 2 pi n, where n is an integer. So our final answer, we're going to have theta equals pi over 3 plus 2 pi n, where n is an integer. And our second answer, theta is going to be 5 pi over 3 plus 2 pi n, where n is an integer.